Welcome to the explainer. Look at this equation. 3x to the fourth minus 7y to the fifth minus 86 equals 0. In physics and economics, variables rarely sit on opposite sides of an equal sign. Here, they are bound in an implicit function. Finding the exact rate of change, the derivative, of a structure like this using the long-form definition of limits creates a massive computational burden. It requires pages of manual algebraic expansion. Instead, mathematicians prefer a more efficient path. They use a toolkit of algorithmic shortcuts known as the rules of differentiation. By the end of this video, you will have the specific rules required to deconstruct this expression and find its derivative in just 2 steps. Let's start with the negative 86. A constant number like this represents a static state. Because it doesn't move or grow, it contains no change. This follows the constant function rule. Because a constant is static, its rate of change, its derivative, is always exactly 0. Next, we look at 3x to the fourth. To measure a variable raised to a power, we use the power function rule. You drop the exponent, the 4, down to multiply by the coefficient, then reduce the original exponent by 1. 3 times 4 gives 12x cubed. These rules handle static values and basic variables, but real-world systems often involve variables that interact with one another. This text outlines the product and quotient rules. When functions multiply or divide, we use these algorithms to track how their combined rates of change evolve. The final term in our equation is 7y to the fifth. This is more complex because y is a composite function, a function nested inside another. We resolve this with the chain rule. We differentiate the outside structure first, bringing the 5 down to make 35y to the fourth, and then multiply it by the derivative of that inner function, which we write as dy over dx. By addressing these nested layers, we can now solve the most complex part of our original equation. Now we apply these rules across the entire expression simultaneously. This process is called implicit differentiation. The 3x to the fourth becomes 12x cubed, and the negative 86 drops to 0. Applying the chain rule to the final term gives us negative 35y to the fourth times dy over dx. By following these steps, we have bypassed the manual labor of limits and successfully differentiated the implicit structure. Finally, we use basic algebra to isolate our target. Moving the terms across the equal sign shows that dy over dx equals 12x cubed divided by 35y to the fourth. Our result matches the mathematical proof shown here in example 16. By applying the rules of differentiation, we reached the final solution with far more efficiency. This system is iterative. We can take the derivative we found and apply the rules again. At the top of this source page, you see second and third order derivatives. This process allows us to measure the rate of change of the rate of change. In engineering, this is how we track acceleration. Whether we are analyzing shifts in economic markets or calculating the thrust of a rocket, higher-order derivatives provide the data to map that acceleration. Calculus is a system of logical abstraction. It replaces manual calculations with reliable rules that describe the behavior of the world around us. With these tools, you can analyze the mechanics of increasingly complex systems. Thank you for watching. Allah Hafiz.